Hello, I'm Jim Harter. I'd like to give this presentation to show an example of how AFGROW Spectrum Manager could be used to create a usage spectrum for, in this case, my personal T-18 airplane, but I hope the steps that I show you here could be helpful to you. So one of the things we hear a lot is, how do we build a spectrum? Do we, if we have data, we have exceedance data, and I thought, let's go ahead and go through an example with the T-18. So I'm going to start by talking about what the T-18 is, give you an overview, some historical information, go through the process that I went through when I bought the airplane, reassembled it, made some repairs, show you the first flight, and then walk through all the steps, the weight and balance, the wing loading calculations, the critical control point details, the geolimitations on the airplane, and the Dynon HDX electronic flight information system that I use to collect the flight data, and then go through the process of creating the spectrum, looking at data sampling effects, a life prediction, talk a little bit about friction effects, and then end up with a nice, hopefully nice, relaxing flying video. So let's talk about the T-18 quickly. The T-18 was an early two-place experimental airplane designed by John Thorp. His first flight was in 1963. The cruise speed on the airplane is between 130 and about 174 knots, or about 150 to 200 miles an hour. The never exceed speed on this airplane is 200 knots. It uses anything from a Lycoming 0290 to an 0360. My particular airplane uses a 0320, 150 horsepower. My maximum gross weight is 1,500 pounds. My fuel capacity is 27 gallons. The range is approximately 450 miles. There's been 400 of these airplanes built. Now here's some facts that might be interesting. This was I guess one of the first all-metal two-place side-by-side high-performance airplanes. It used matched hull construction, so jigs weren't required. It uses a horizontal stabilator instead of a stabilizer and elevator. That was a hallmark of John Thorp. He employed a counterweight system on the stabilator to balance the stick force, also to avoid flutter. There were some flutter issues with the early airplanes, and they ended up doing flutter testing to be good up to 230 miles an hour. The first home-built airplane to fly around the world was the T-18. Of course, it obviously had to use auxiliary fuel tanks, but it did fly around the world. It was also the first home-built airplane to fly to both magnetic and geographic North Poles. And both of these feats were done by the same airplane that's now hanging up in the EAA museum. So, back to my airplane. In March of 2017, I found this airplane in California, Apple Valley Airport, and a good buddy of mine, Jason Scheike, flew out with me to pick it up, and the other fellow there on the right is Skeeter Wyman. He was the owner. We picked it up put it in a truck, and you can see loaded it up, and headed back. One of the things I'll mention though, I'm also building a midget Mustang, and I've been meticulous with it, but Jason pointed out to me, he said, "Jimmy, this airplane's got 160 hours on it. Don't sweat every detail, just put it together, get it in the air." So we hauled it back, and we were headed east. And when we got back, you can see how it looked. So that was the state it was in. So some reassembly was definitely required. Now, as I started putting it back together, I started to find some issues. Even though Jason had told me don't sweat the details, I ended up finding some details I really wanted to fix. So here you see an example of some double drilled holes in the aft bulkhead that I really didn't want to keep there. And also I really wanted to add some access panels to get back there so I can install that stabilator more easily and also do inspections more easily. So there you see the repair on that aft bulkhead with a reinforcement in the lightning hole in the back. So I fabricated a new skin with access panels, as you can see on the left, and then installed it back on the airplane on the right. Now, as I started putting the stabilizer on, you can see I was doing my Fred Flintstone imitation there on the left. You can see the counterweight on the right for the stabilizer is one of the anti-flutter and also to control the stick force. You also can see some lead weights on the tips of the stabilizer. That was also needed for flutter relief. Now, on the vertical tail, I made a new vertical tail because I wanted to include a VOR antenna for navigation. You can see the antenna on top on the left, but so I had to built a new fin, and then I had to then build a fiberglass cap on top of the fin. Also, there were no access panels in the wings, so I took some time and put access panels in both the inner and outer wings, and also in the fuselage. Now, redid the instrument panel completely to allow room for radios and transponders, and the space is very limited on this airplane, so I tried to make use of every little bit of space by bending that instrument panel a little bit to allow me to have clearance for the radios. Also on the right, there's the engine. The engine had unknown number of hours, and so I asked Jason if he would pull one of the cylinders and look inside to see if he saw any issues. And he didn't, so we put it back together, put it on the airplane. Now there it is on the airplane. Also the baffling for the cylinder cooling was damaged on both sides, so I remanufactured some baffles, and I added a little bit more strength. I put a flange at the top, so there was very little room to attach the baffle seals. By adding the flange there, it gave me extra edge margin that I really needed, and also stiffened it up quite a bit. And on the right, you can see the wing being installed on the airplane, and you can see how the outer wing attaches to the inner wing. Now the fuel tank, I was really concerned about the fuel tank. The reason why the airplane was taken apart was because the original fuel tank was fiberglass, and it leaks, so it all had to come apart. And this is the new aluminum tank that Skeeter had built, and I wanted to make sure that it had no leaks. And then I also wanted to install a fuel sender, so I cut it open and added the fuel sender to the top of the tank. Also, I added an additional fuel vent because I thought that at some point I might try to have wet wings and then pump fuel back in from the wings into the tank. So that's what the extra port is really for. But right now it serves as an alternate vent. Now, you can see on the left the fuel valve. The original fuel valve was at the bottom of the tank, which is impossible to reach when you're sitting in the airplane and flying. So I really wanted to bring that forward, so I brought it forward. As a result, though, it then required me to use an electric fuel pump because gravity feed didn't allow enough pressure because of the losses involved in taking that extra route to that fuel valve. But I think it was worth it, at least I could reach that valve in flight if I ever had to. Also, I made new fiberglass fairings for the gear legs. That took a little bit of time. And then installing the pitot-static system. This particular one is a Dynon with an angle of attack, and you can see how it's installed along with the access panel there in the outer wing. And then getting close to the end of the rebuild, I put in boots for the control sticks, and these came out of a company that built parts for the RV6, which is very similar in size to the T-18, but I had to build some support structure to work with my airplane. And then on the right, you'll see a little bit of the autopilot control servos, and I'll show you a better picture of that here in a second. There's the first Dynon HDX panel going through tests of the instrumentation. making sure that all worked. And on the right, the control stick with the trim switch, and then on the left of there, it's not in there right now, but the push-to-talk switch for the radio. Now on the left, you'll see a little bit more of the autopilot setup. You can see how the controls work for the, on the lower part, you'll see the control for roll, and then the upper, you'll see control for pitch, and some of the wiring that was involved. And then finally, when sticks are installed, switches are in place, the first panel is in, and on the left, you see the mag switches, and on the center there in the low, you'll see all the other switches control the lights and the master avionics radio. And then below that is the mixture control and carburetor heat. And you can just see it on the left there, the throttle. So finally, first flight after the reconstruction was August 19th, 2023. My oldest is a airframe and power plant mechanic, so he was able to come out and look over all of my work, make sure that everything was safe, and sign me off as airworthy. And then he became a crew member on their first flight. I'll show a video of the first flight, a quick video to see the takeoff and landing at least of the first flight. All right, so there were a few issues on that first flight. The first was the biggest one was we had some high cylinder head temperatures, and there were some air leaks in the upper cowling, so I had to go back and added some more seals and restricted some airflow through the oil cooler to borrow air from the oil cooler to switch over into the cylinders. There was a slight right roll tendency, and I adjusted that by just fixing the flat cables to kind of allow a little bit of down force on the right side to account for that rolling to the right. And then there was also a slight left yaw, and that was because there was a twist in the rudder. The original builder had put a twist in it, so I put a trim tab on the rudder, and that fixed that problem as well. Okay, so here's a picture of the modifications, additional seals. You see another view of the seals, modifications. I restricted some of that flow into that oil cooler, and you can see on the right there was I added the trim tab there. Okay, so all airplanes have an operating handbook giving you all your limitations, your airspeeds, everything. So the summary here gives you the performance numbers. The VX is the climb. It's the steepest angle of climb, the best rate of climb, and so forth. Different airspeeds for the airplane there. Now here's the weight and balance we need to have to actually be able to calculate all the loads in the wing. So you can see the airplane length, distance from the datum to the main gear and to the leading edge of the wing, which was what I used to measure everything off of. So here's the official weight and balance sheet. Empty weight on this airplane is 915 pounds. Gross weight, 1,500 pounds, leaving a useful load of 585 pounds. You can see the weight and balance datum was the wing leading edge. It's station 55. And empty weight puts me at station 61.92. And the allowable CG range of this airplane is 62.5 to 72. So with the weight in the pilot passenger seat brings us right within the weight and balance of the airplane, proper CG range. The fuel station is station 50, pilot passenger is station 86, and the baggage is station 109. So in order to calculate the total lift in the wing, you have to take the total weight of the airplane, the gross weight of the airplane, and then you have to account for the fact that the horizontal stabilator has a downforce. So you calculate that downforce by looking at the moment arms between the wing center of lift and the horizontal center of lift, and then you can calculate then what the total wing load would be. So that's what you see here on the right. Now I made an assumption on the wing lift distribution, pretty simple assumption, assuming uniform lift. It's a constant chord wing, and you get the lift drop off as you get to the tips, and so I just assumed that drop off happened about 8 inches before the tips, right where the wing tips are, the fiberglass wing tips. So that made it simple because I used the rectangles and triangles to calculate the lift and the moments. And you see the total wingspan is 20 feet and 10 inches. And so to calculate the running wing load, you can see you divide by 240 because those two triangles would take half the area. So I took off that 10 inches for each wingtip, not 8 inches. The outboard wing has got a 8-degree dihedral for stability. Excuse me. Now to find the load in that lower lug fitting you see there in the picture, that's my critical point I was looking at in this case. That wing attach for the outer wing, you can calculate the force, total force, as a running load, and you multiply it by 49.5 plus the 10.1 over 2, which gives you the area of that triangle on the outside. And then calculate the outer lifting moment, and then the lower bolt shear. So you have the shear and the moment to calculate what the total load is in that lower pin. So here's some pictures. I don't know how well they came through, but this is showing the outboard wing spar and the fitting with the lug attached, so you can see the dimensions there. Now here's a more simplified picture calculating that pin load using the wing shear, and then the moment you calculate the total load, and then we can relate that right back to G loading if you know what the weight of the airplane is. So the static G limits on this airplane, one of the things you'll see on the left, and I hope it's visible to everybody, but someone had written to John Thorp asking what the limits of the airplane were in terms of maneuver limits. And so he wrote back and gave it different gross weights what the G limits were. So I went to go back to see, with my assumptions, if I would be able to duplicate his numbers. And you can see here it was amazing, they came out exactly the same. So he must have assumed that that lower bolt was a critical structural point for ultimate failure. And then he showed that at we have here at 1,250 pounds, we have an upper positive G limit of 6, and then at 1,500 pounds, the max positive G limit was 5, and that again matches John's calculations exactly. So I felt pretty good about having those assumptions fairly accurate. Now, if you want to talk about different categories of flight and what the G limits are, for a normal category airplane, you'll have a positive limit of 3.8 and negative limit of 1.52. And then utility category brings you up to 4.4 positive and negative 1.76 negative. Aerobatic gives you 6 positive and 3 negative. For this airplane, I was not interested in anything but normal category. This is a point A to point B airplane, but I wanted to show some of the limits. So whether or not you could actually exceed any of these limits with this airplane is very difficult to do. I have an upper example with a forward CG limit and the bottom example with an aft CG limit. And it shows that if you have a total of 110 pounds or more of pilot and passenger weight, or less than 455 total pounds, and a baggage limitation of 70 pounds, my airplane can never exceed either the CG or the normal category static social limits, and it also remains clearly within the utility category limits. All right, so if I looked at residual strength requirements, so what would be the highest load I would get at that lower wing bolt based on my highest worst case situation with the most forward CG, and that limit comes out to be roughly 60,000 or 60 KSI plus. That becomes my residual strength requirement for the crack growth analysis, saying that that airplane has to be able to show it can contain that load at all times. So that's how I calculated that value. Now here's a picture with both Dynon Skyview HDX displays in the airplane in flight. It's a very nice system. So I want to quickly discuss some of the capabilities of the Dynon system. You can see on the left, you've got your virtual graphics here, the virtual terrain. We've got airspeed, altitude, HSI for heading, engine instrumentation, control, the autopilot, transponder. It's got a timer. You see all the controls are all touchscreen. When you go over to the right, you see it has traffic overlays. It'll tell you traffic, relative speed, direction, distance and altitude in hundreds of feet from where you are. And finally at the lower right, you'll see possibly you can get the weather overlay as well. So it's a very capable system. It records a number of pieces of information. You can see here we have everything from time to magnetic heading, airspeed, turn rate, pressure, altitude, angle of attack, vertical speed, your vertical and horizontal Gs, your autopilot information, transponder, engine data, everything you could ask for, your Hobbs time, your attack time. So everything's recorded inside the system, and you can select the recording rate. The default is 4 samples per second. So I use this information to develop a spectra. So in this case, you go to the airplane, you insert the thumb drive into the system, you download the information as comma-separated variable files, which will be go right into Excel, and then you have the data in Excel. Then I wrote a script to extract the data I needed to calculate the loads, and then read that in the Spectrum Manager, cycle count the information, and then go to AFGROW and do the life prediction. So when you export the data, you can see there's a couple screens. You simply go through, insert the thumb drive, tell it you want to export the data. It runs data back to your thumb drive. And then there's an example in Excel. There's 103 columns of flight data. And sampling at 4 hertz, you can imagine that there's lots of rows of data that you'll get there corresponding to 1/4 of a second each. So in this case, I extracted the GPS data, which told me the date and time, the system time, the indicated airspeed, pressure, altitude, vertical acceleration, true airspeed, fuel remaining, which I needed to get the total weight as a function of time, Hobbs time, which is the time since the instrumentation was turned on, and takt time is a scaled time based on the engine RPM. And then I had to include, after the flight, pilot weight, passenger weight, and baggage weight to actually calculate the weights. And I used indicated airspeed to determine when we had weight on and off the wheels. So I used greater than 62 knots was in the air. Less than 62 knots was weight on the wheels. Greater than 70 knots was weight off the wheels. So that's how I determined when I had load in that lower lug. Once you're on the ground, there's very little load. The actual upward wing doesn't weigh very much anyway. So there's really no loading to speak of on that pin unless you're in the air. So here's how I set up the scripts. There's a script to extract the data. So pushing that button to extract the data takes the data out of the page with all those 103 columns of data, and then writes it back into a page. So it's smaller to deal with. You just have the data you want to work with on that screen you see there. And then there's a button to calculate the loads, but before you use that script, you have to fill in that yellow area, which is the pilot weight, the passenger weight, and the baggage weight. So that, along with the fuel weight, which is calculated 4 times a second, it will then be able to calculate what the total weight of the airplane is, and then it goes through the calculations you saw earlier to calculate what the pin load is in that lug, based on the load distribution, the total load in the wing, and so forth. And then that final button, the cycle counting button, is a script that goes to Spectrum Manager. Now the Spectrum Manager is COM-enabled. Then you can use a script to take the loads out of this spreadsheet, run them in the Spectrum Manager, cycle count those to get the cycles, and then create a loading spectrum, actually create a subspectrum. Each flight would be a subspectrum in this case. So we had, I think the first spectrum we had, I think around 30 some flights, developed a whole spectrum, and you'll see that shortly. So here's flight number 1. Now these are reversals. Reversals being when we have a minimum and a maximum. They're not necessarily cycles, they're peaks and valleys. So when the load direction reverses and you take that sampling rate of 4 hertz and you find your peaks and your valleys, and these are plotted here. And then when you go to cycle counting, there's different ways to cycle count. The method used in AFGROW has been there, since about the late 80s. It was a method that was used at Northrop when I worked at Northrop, and I modified it over the years. Back then there was no cycle counting standard. Now there are ASTM cycle counting standards, a range pair method and a simplified array and flow method. And on the left you'll see the benchmark from the ASTM standard, and then the results of that benchmark with a different method. So each one of those methods produces a slightly different cycle counted spectrum. But when you go and look at flight 1, for example, and you do that cycle counting based on the current method in AFGROW versus the range pair or simplified array and flow, they happen to turn out identically the same. That just has to do with how the data cycles about the 1G. So in that previous case, that was the benchmark. That's not a typical kind of thing you would see from a G recorder, for example. But that is the benchmark that's used in the standards, so I'm showing that here. But when you get to these these type spectra, it turns out that all those methods ended up with the same result. So here is a picture of the spectrum the 4 Hertz sample spectrum after it's been cycle counted in AFGROW. And you can see the exceedance plot is shown, and you can see the actual, that lower window, you'll see the actual spectrum plot for all the flights in that sequence. Again, 30, I think it was 30 some flights. Now we go through and take that information, you put it into AFGROW, and we'll use the lug model, and then we'll set the spectrum multiplication factor to 1, because we actually have the loads, the actual bearing loads in the spectrum. And then you'll see the residual strength requirement that we talked about earlier that sets the load of the bearing stress that has to be carried at all times, and then do the life prediction. So you can see here, based on that spectrum, we're showing that we have approximately 2,700 flight hours, and you can see now that I also recorded whether or not we were in climb, we were in level flight, or we were in descent, or we had the max ground-to-ground cycle, so we could see how that damage was distributed. So in this case, you can see that the majority of the damage was caused by the level flight, which you kind of expected would be, less caused by the gag in this case. But the nice feature is being able to actually summarize the damage within AFGROW now. And now we also have the damage by flight, so you can look at all these flights and you can see what was the percentage of total damage caused by each one of those flights. Now, also I want to look at sampling rate effects, because when you look at the data, the reversal data, here's a sample of about roughly 23, 24 seconds of data, and you can see that there's some gaps. So it looks like 4 Hertz sampling rate wasn't quite enough. Probably should have had higher sampling rates. So if we looked at what happens when we go to 8 Hertz and recorded data over the same period of time, you can see it's a little bit better capturing the peaks and the valleys, but you still see some dead spots. And going up to 16 Hertz, much better. There's a couple little glitches, but actually in this case that was the fastest I could go with this system, but still looked like it was pretty good. 16 Hertz seemed like it was capturing everything. So I went back and repeated this now with 5 flights, recording at 16 Hertz to see what I got. So here is cycle counted flight data, bearing stress. This was 4 Hertz. I was showing about 0.933 cycles per second. And then at 8 Hertz we got 1.9 cycles per second, and going up to 16 Hertz we ended up with 3.37. So we were definitely, looked like we were missing cycles at the lower recording sampling rates. So repeating this again at 16 Hertz made a lot of sense. And I also took these data and compared it to the general aviation aircraft information from the FAA. That was a publication for normal acceleration data, published in February of 1993. Everything was in terms of the normal acceleration load limit factor, and so for my airplane that comes out to be 2.033, and that's based on your wing loading, your wing aspect ratio, this concept of M, and your cruise speed, because everything is also given in terms of cycles per nautical mile. And then there's a factor K that comes into play. But in the end, the normal acceleration load limit factor for my airplane is 2.033. Putting that back in, I plotted their 95% versus their mean acceleration data compared to what I got off of the airplane. And you can see it compares fairly well. The publication didn't go low enough on the G's to capture the total curve, but you can see it came out pretty close between the mean and the 95%. So here's the 5-flight spectrum sampled at 16 Hertz, quite a bit different. Redoing this analysis again, you'll see we get shorter life, 1490 per flight hours, and the breakdown is quite different as well. So how much of the damage was caused by level flight or climb, descent, or gag. Again, this was just so you could see how you could do anything you'd like. If you would like to tag any part of your spectrum, you can do that, and then AFGROW will then keep that in your spectrum after it counts it, and then you'll see the result when you run the life prediction. You can see how much damage was caused by anything you've tagged in your spectrum. And at the bottom right, you see the damage by flight for all 5 flights. The 3rd flight was the most damaging, and that was kind of apparent. When you look here, you can see that flight, that 3rd flight there, looks much more damaging than the other 4. Okay, finally, I wanted to talk a little bit about friction in this case, because when this airplane was put back together, I used NAS bolt, close tolerance bolt, because I knew this was going to be a critical area and I wanted to get the most life I could. So I used the NAS high strength bolt. It has a maximum tensile strength of 17.1 kips, and an AN bolt is not quite as strong, so I could torque that down pretty good. And if I assumed that I had 75% of the yield in that compression, it works out to a clamping force of somewhere at least of 9.6 kips. And then with assuming a coefficient of static friction of 0.3 for so-called greasy aluminum to aluminum, you get a shear force of 5.77. That's the worst case. So if you had the worst situation with a greasy aluminum to aluminum, we would expect to be able to carry 5.77 kips in that part. And that works out to be 41.14 KSI, which is about double the stress I've seen in any one of those flights. So that indicates that so far that life prediction is probably way low. You'd have to do a test to verify that, but I felt very comfortable that the airplane is going to have a long life. The only thing I did not do, I should have taken the same calculations and looked at the AN3 bolts, the row of AN3 bolts that transfer the load from the fitting into the lower spar, because there you don't have the same amount of clamping force because the AN3 bolts don't have that kind of capability. So I'll maybe go back and do that at a later point. But at least in this plate, you can see exactly the process you could follow to create a spectrum if you have the recorded data like this. Finally, just wanted to say that this presentation was intended to demonstrate how I use Spectrum Manager to build a spectrum. You'll be different. Every location's different. I just wanted to go through the process. I also want to point out that there was some noise, approximately plus or minus 0.1 G in the recorded data. So there's always going to be some error there. But at least we still illustrated the typical steps that could be taken to build a loading spectrum for damage tolerance analysis. And as I said, we have friction, and I know we have friction. A lot of times we don't account for it. In this case, there was a tremendous amount of friction that I could take advantage of here. Now, as I said, this would move the critical location, if true, to the row of 6 AN3 bolts along the upper spar from that fitting. But to be sure, you would always have to run a test. There's just no way to be sure without validating this. And again, I hope this presentation was helpful, or showing you how Spectrum Manager could be used to create a loading spectrum for growth life prediction. And to end this, I'd like to just take a couple minutes and show you a nice flight that I took on this airplane with another friend, and we'll go out with that.